We're now going to look at refrigerators. Refrigerators are a lot like heat engines but run in reverse. So a refrigerator is something which uses work to remove heat from a cold reservoir and put that heat into a hot reservoir. So some refrigerators that you'd be very familiar with is the fridge in your kitchen. With a fridge in your kitchen, the inside of the fridge is the cold reservoir. The engine on the back of the fridge, the motor, does work, and that moves heat from inside your fridge to outside your fridge. So the surrounding room is the hot reservoir in this case. Another example is an air conditioner. With an air conditioner, this does work to remove heat from the room to outside. So with engines, it was useful to look at what we meant by an ideal engine. It's also useful to do this for refrigerators. So in an ideal refrigerator, all processes are reversible and there's no wasteful energy transfers. So for example, there's no friction, turbulence, or air resistance happening, which will use up some of the work to not useful processes. So an example of an ideal refrigerator is shown here. This is actually known as a Carnot refrigerator because if you look at it, it's probably very familiar to you. This is just the Carnot engine acting in reverse. So we're doing work, we're putting work in to remove heat from the cold reservoir and put heat into the hot reservoir. So let's look at the efficiency of our refrigerators. Now, the whole aim of a refrigerator is to remove as much heat as possible from the low temperature reservoir and do that for as little work as possible. So the efficiency of a refrigerator is defined in the same way as the efficiency of an engine, but we will end up with a slightly different equation. So we'll give it a little bit of a different symbol to stop ourselves getting confused. So we'll give it the symbol capital K, and capital K we'll call the coefficient of performance. So for a refrigerator, the coefficient of performance is equal to what we want divided by what we pay for. Now in this case, what we want is as much heat as possible being removed from that refrigerator, so inside the refrigerator. So we want QL to be as large as possible, and what we pay for, well, that's the work that we need to do to move this heat. So what we pay for is W. So let's have a look at how we can calculate this coefficient of performance for our Carnot refrigerator. For our Carnot refrigerator, as you can see from the diagram, the absolute value of the work plus the absolute value of the heat transferred from the lower reservoir is equal to the heat transferred to the top reservoir. So that tells us that the absolute value of the work is equal to the absolute value of QH minus the absolute value of QL. So substituting into our equation, we end up with K is equal to the absolute value of QL divided by the absolute value of QH minus the absolute value of QL. Now for any cycle, including this one, the change in entropy around the entire cycle is 0, and as this is a Carnot cycle still, it's just going in the opposite direction, we've got 2 adiabatic and 2 isothermal processes. There is no heat transferred through the adiabatic processes by definition. So if we want to consider entropy again, we know that the entropy transferred when heat is being removed from the cold water bath must be equal to the entropy transferred to as the heat is transferred to the hot water bath. So once again, we can use entropy, which remember entropy for an isothermal process is equal to Q over T, to write QH, the absolute value of QH, divided by TH is equal to the absolute value of QL divided by the absolute value of TL. And so those are just the magnitudes of the change in entropy over the two paths for which it's not 0 need to be equal to each other so that they can cancel each other out. Okay, so using this expression, we can write our expression for K, the coefficient of performance, in terms of the temperatures of the high temperature reservoir and the low temperature reservoir as K is equal to TL divided by TH minus TL. So I'll leave this as a little exercise for you to try. Then to give you an idea of the kinds of magnitudes that we're talking about for these efficiencies, these K values, for a typical air conditioner, it would have a K of around about 2.5. And a typical fridge would have a K of approximately 5. Now, you may be thinking, wouldn't it be great if we could design an absolutely perfect refrigerator in which we didn't have to do any work and we could just transfer the heat from the hot reservoir up to the cold reservoir? Okay, so what we're going to do now is consider the entropy changes in a process such as that. So here you can see a schematic of that process. There's no work involved. We're transferring heat from the low temperature reservoir to the high temperature reservoir, and the working substance is undergoing a cycle in this process. Now, rather unfortunately, it turns out that this is actually impossible. But let's go about showing that now. Now, for the working substance itself, there is no change in entropy around the cycle because entropy is a state function and it's coming back to where it started. Okay, but we need to consider the entire system if we're going to consider entropy changes and apply our second law of thermodynamics. So in this system, we've also got the cold reservoir and we've got the hot reservoir. So the cold reservoir is giving heat Q to the working substance. So as it does that, we can say that the change in entropy of that process, let's call it delta SL, is equal to Q over TL. And this should have a negative sign because the heat is being transferred out of that cold reservoir. And now the heat is being transferred in to the hot reservoir. So the change in entropy of that process we can write as Q over TH. And so we'll give delta S, the symbol for that process is delta S subscript H. Okay, so the total change in entropy is just the sum of these two. So we've got Q over TH minus Q over TL. Now, TL, that was the low temperature. So TL is smaller than TH. So you can see that in this expression, we're subtracting a bigger number from a smaller one, and so we're going to end up with a negative change in entropy. So this process is actually forbidden by the second law of thermodynamics. So the second law of thermodynamics actually tells us that we cannot have a perfect refrigerator. So another way to state the second law of thermodynamics is that no series of processes is possible whose sole result is the transfer of energy as heat from a reservoir at a certain temperature to a reservoir at a higher temperature. So right at the beginning when we were learning about thermodynamics, we said that heat is always transferred from a warmer body to a colder one. And now we know why. If that wasn't the case, we'd be breaking this second law of thermodynamics.